Hey everyone, welcome to this Silvaco TCAD simulation tutorial. In this video, I will demonstrate how to perform the simulation of semiconductor material defects. Specifically, I will focus on how various types of donor and acceptor-like defects influence the electrical properties of a material. We will explore key parameters like tail distributions and Gaussian distributions of defects, and examine how the density and energy level of these defects affect the overall carrier generation and conduction properties. So as an example, I'm going to demonstrate the Silvaco TCAD simulation of two silicon PIN solar cell structures, one without including the defects and second with including the defects, and then we can compare the performance parameters of these two different kind of solar cells. So I am demonstrating the example of a solar cell, but you can actually implement it in any kind of devices. You can implement it in LEDs, or you can also implement it in transistors, in applications relevant to your own kind of research. So since in today's video I'm focusing on silicon PIN solar cells, let me talk about the basics of silicon PIN solar cells and the kind of defects associated with silicon based solar cells, and then I'm going to demonstrate the simulation. So what are different defects in silicon? Defects in silicon can originate from impurities, high temperature processes, or structural disruptions in the crystal lattice. They significantly influence the electrical properties of devices by introducing trap states inside the band gap, which affect the carrier recombination and trapping. Now, there are different types of defects in silicon. For example, acceptor defects. We can call them deep acceptors as well. As an example, oxygen vacancy complexes, transition metal impurities, for example, iron and copper. Now, how do these acceptor defects form? Oxygen-related defects form during crystal growth or high temperature oxidation. Similarly, transition metal impurities originate from contamination during processing. The impact of these acceptor defects is that they actually create deep energy levels inside the band gap, acting as recombination centers and reducing the carrier lifetime, which further reduces the performance parameters of different kind of devices. Secondly, there could be donor defects as well. For example, shallow donors. Examples are phosphorus and arsenic doping. And the formation of these kind of defects occur by the introduction of processes such as ion implantation or diffusion. Now, these ion implanted atoms or diffused atoms may interact with oxygen in oxygen-rich silicon to form donor-like states. And the impact of these donor defects is that these provide free electrons in N-type silicon and improve conductivity. There could be also generalized defects, for example, mid-gap defects. Example of mid-gap defects are vacancies, interstitials, silicon-oxygen complexes. They are created during the crystal growth, annealing, or ion implantation. Stress or radiation displaces the silicon atoms, forming point defects. The impact of this is that it leads to mid-gap states that act as electron or hole traps, increasing the recombination. So this video is ideal for those looking to understand the underlying physics of defect modeling in semiconductor devices and how to interpret the results of such simulations to predict material behavior under different conditions. So let us get started. As I already mentioned that I'm going to simulate two structures, one without defects and the other one with defects. So first let me introduce you to the silicon PIN solar cell structure without defects. Let me show you the structure first. So here is the silicon PIN solar cell structure. We have the anode at the top, the cathode at the bottom. The structure runs from 0 to 10 micrometers along the x direction and from 0 to 20 micrometers along the y direction. If we look at the doping distribution across this structure, I'm actually looking for net doping. Now I'm going to show this figure to you later as well, but what I did is I introduced a really thin p-type layer over here at the anode, and then another thin n-type layer over here at the cathode, and in between I have introduced an I layer which has an n-type doping of 10 to the power of 14 per centimeter cube. So basically I'm forming a silicon based PIN solar cell structure. Now let us go to the code part. So first I will show you the code for the silicon PIN solar cell without the defects, and I already posted a lot of videos on the simulation of solar cells, so I'm not going to go into the nitty-gritty and the intricate details of all the code. I'm just going to run through the code block by block. So I'm starting one block of Atlas Silvaco TCAD. Here I defined the meshing. The meshing is running from 0 to 10 micrometers along the x direction and from 0 to 20 micrometers along the y direction. In order to see the meshing, we click on this icon, hit apply and click OK. So we have got denser meshing over here at the close to the top and also here at the bottom at the cathode interface, and we've got sparser meshing in the middle. Then I'm introducing region number 1. The material is silicon. I'm introducing anode at the top of the structure and cathode at the bottom of the structure, which you can also see over here. Here is the anode and here is the cathode. Then I save this structure with this name, and then I start working in another module of Atlas. I call the previously saved structure, and here I introduce doping. So I'm introducing a doping level of 1 into 10 to the power of 14 per centimeter cube for the entire structure, and then I define a peak hole concentration at the top of the structure, and it's basically has Gaussian distribution peaking at a y value of 0 micrometer. So as you can see over here, a thin layer of hole concentration here at the top, and then another thin layer of electron concentration with a peak carrier concentration of 5 into 10 to the power of 18 per centimeter cube at 20 micrometers. So a thin layer of hole concentration over here at the top, a thin layer of electron concentration over here at the bottom of the structure, and an I layer in between these two thin layers, forming the PIN structure. Then for silicon, I'm defining some basic material properties. More importantly, I am calling the SO profiles, which has the refractive indices and the absorption coefficients information saved in this file. So in this file, so I just have to call this file, and then I'm introducing some models. Using a method, and then I want to output some different parameters. Here I am saving the structure under thermal equilibrium initially. In this block, I want to look at the IV characteristics of the solar cell from 0 to 0.55 volts. under dark conditions, and then I introduce illumination under AM 1.5 conditions, ramping up the light intensity initially from 10 watts per meter square to then 100 watts per meter square to then 1000 watts per meter square. And here I'm actually running a sweep under light conditions from 0 to 0.55 volts, and then I plot the IV characteristic under both dark and light conditions in the same figure, and I'm going to demonstrate it later. In this block, I'm going to perform the simulation of the output parameters. So I'm going to show you the short circuit current density, open circuit voltage, fill factor, and efficiency of the solar cell. Then I started working another ArcList block. So I import the previously saved structure once again, and I define the basic material parameters, etc. once again. And here I want to look at the internal quantum efficiency, external quantum efficiency in a wavelength range of 0.3 to 1.5 micrometers with a step of 0.01 micrometer. So this is the solar cell, this is the code for the solar cell structure without defects. And then I've also saved a code, created a code for a solar cell with defects, and the code is going to be the same, except that after defining the material parameters, I am introducing the defects over here, and also later in this block where I want to look at the internal and external quantum efficiency of the solar cell. So since the focus of this video is going to be on the defect simulation, so let me explain this part in more detail as compared to the rest of the code, because you can easily find the rest of the code in the other videos that I already posted on YouTube. So the parameters in this Silvaco TCAD code describe defects that affect the electronic behavior of silicon in the simulation. Specifically, the defects are associated with acceptor type defects, donor type defects, and generalized defects. These defects can influence carrier recombination, trapping, and the overall electrical properties of the semiconductor device. Now here is the breakdown of different types of defects that I actually introduced in this code over here. The first parameter NTA specifies the density of acceptor-like states in the tail distribution at the conduction band edge. This defines how many acceptor-like states exist in the tail region of the acceptor-like states distribution near the conduction band. So the value of 1 into 10 to the power of 16 per centimeter cube over here suggests a significant number of acceptor-like states that contribute to whole generation favoring p-type behavior. And then I have introduced NTD, which specifies the density of donor-like states in the tail distribution at the valence band edge. This defines how many donor-like states exist in the tail region of the donor-like states distribution near the valence band edge. And a value of 1 into 10 to the power of 16 per centimeter cube over here suggests a significant number of donor-like states that contribute to electron generation, but their contribution is less significant than the acceptor-like states in this case because of the upcoming parameters over here. Generally, for silicon, the value of NTA to NTD, since silicon is a more mature material, would be in the range of 1 into 10 to the power of 14 to 1 into 10 to the power of 16. I've introduced the higher end of these defects so that we can visibly see the difference between these two codes, one with the defects and another one without the defects. Now let us focus on this parameter WTA having a value of 0.33. WTA specifies the characteristic decay energy for the tail distribution of acceptor-like states. This defines how the energy of acceptor-like states spreads near the conduction band. A higher value means the acceptor states extend more deeply into the conduction band, influencing the ionization of acceptors and thus the hole concentration. Similarly, WTD having a value of 0.05 electron volts specifies the characteristic decay energy for the tail distribution of the donor-like states. This defines how the energy of the donor-like state spreads near the valence band. A smaller value as compared to WTA means the donor states are more localized near the valence band and less spread out, affecting the electron donation. Then we have this parameter NGI is equal to 1.5 10 to the power of 13. It specifies the total density of acceptor-like states in a Gaussian distribution. This indicates how many acceptor-like states are present in the energy region defined by the Gaussian distribution. Similarly, we have NGD specifying the total density of donor-like states in a Gaussian distribution. Its value is 1.5 10 to the power of 13 once again. Similarly, EGA has a value of 0.62. It specifies the energy corresponding to the peak of the Gaussian distribution for acceptor-like states. And this energy is measured from the conduction band edge. So in this case, EGA is equal to 0.62 electron volts means that the acceptor states are located 0.62 electron volts from the conduction band edge. Similarly, EGD is equal to 0.78 over here. Electron volt specifies the energy corresponding to the peak of the Gaussian distribution for the donor-like states. And this value of 0.78 electron volts is actually measured from the valence band edge. Similarly, WGA specifies the characteristic decay energy for the Gaussian distribution of acceptor-like states. This defines how the energy of acceptor-like states is spread around EGA. A smaller value means the Gaussian distribution is narrower, focusing the acceptor states in a smaller energy range. And WGD over here specifies the characteristic decay energy for the Gaussian distribution of donor-like states. This defines how the energy of the donor-like states is spread around EGD. Then we have these parameters. This parameter specify the capture cross section for electrons in a tail distribution of acceptor-like states, and it describes the probability of electrons being captured by these acceptor-like states. So a value of 1 into 10 to the power minus 16 centimeter square indicates a very small probability. So similarly, I've kept a value of 1 into 10 to the power of 16 for the rest of the parameters as well. I'm just going to define the parameters for you. This parameter over here specifies the capture cross section for holes in a tail distribution of acceptor-like states. Specifies the capture cross section for electrons in the tail distribution of donor-like states. Specifies the capture cross section for holes in a tail distribution of donor-like states. Specifies the capture cross section for electrons in a Gaussian distribution of acceptor-like states. Specifies the capture cross section for holes in a Gaussian distribution of acceptor-like states. specifies the capture cross section for electrons in a Gaussian distribution of donor-like states. Specifies the capture cross section for holes in a Gaussian distribution of donor-like states. So the most defining parameters are these two, because the rest of the parameters are pretty much the same for holes and electrons, or for donor and acceptor states. If I summarize the impact of this block, the entire block, on the performance of the solar cell with defects, these two are the defining parameters. So acceptor-like states dominate due to the relatively larger tail distribution, or you can say this value 0.33 electron volts, and lower energy of the Gaussian acceptor states, EGA over here. So higher value for WTA and lower value for EGA actually dominates the acceptor-like states in the defects distribution across the band gap of the silicon PIN solar cell. Similarly, the donor-like states have a narrower decay width, we can call it WTD, of 0.05 electron volts, and their energy is further from the conduction band, which is EGD, as compared to EG of 0.62. So making the donor-like states less effective in contributing electrons to the conduction band. Similarly, the smaller capture cross sections for all states on the order of 1 into 10 to the power of minus 16 centimeter square suggest that the defect states contribute weakly to the carrier generation. However, the balance of acceptor and donor-like states favors generation of holes, which means p-type behavior, as acceptor-like states are more effective in capturing electrons and creating holes. So because of a higher WTA value and lower EGA value as compared to WTD and EGD, these defect distribution are going to result in a p-type behavior for this structure, which means the majority carriers are going to be holes. So if you revisit the code once again, here for the I layer we have introduced N-type doping concentration, which means electron concentration of 1 into 10 to the power of 14 per centimeter cube. So which means that this structure should demonstrate N-type behavior, and but that is the case without defects. But when we include the defects, because of the scenario developed by different parameters of the defects, with defects this structure is going to demonstrate p-type behavior, and there it is primarily because of WTA greater than WTD, and similarly EGA smaller than EGD, as already described. So it's really crucial that you understand these different parameters of the defects before you simulate the structures. So now what I'm going to do is I'm going to simulate the two structures. This one is silicon solar cell without defects. I'm going to start running the simulation for this one. And this one is silicon solar cell with defects. So I'm going to start running this structure as well. And from time to time I'm going to show a comparison of these two structures. Now the figures which are simulated for the structure with defects, I have included _DEF for these figures. So let me see, like for example this one over here, it has underscore DEF. So the figures which have underscore DEF, it's actually for it actually corresponds to a structure with defects. So now for comparison purpose, let me first show you the carrier distribution across the structure once again. So I right click on the structure, go to display. If you click on this icon, it displays the anode and cathode for you. Then I click on contours, go to define, click on contours once again, and then I click on net doping. Here it is, hit apply, click OK. This is the structure without defects, and you can see that we have high hole concentration. Here is the legend, high hole concentration over here at the top, high electron concentration close to the cathode, and we have 10 to the power of 14 electron per centimeter cube in between these two layers, basically forming a PIN structure where the I layer is actually intentionally n-type doped. Hit apply once again. Now I want to look at the energy band diagram of the two structures, one with defects, the other one without defects. So I click on tools, cut line, draw a cut line across the structure. Here you can see the net doping once again. It's around 5 10 to the power of 18 at the edges and 10 to the power of 14 in the middle. But I'm more interested in looking at the energy band diagram at this point. Hit apply. So we can see the energy band diagram. Okay, and net doping. Let us remove the net doping part for this. Hit apply. Okay. So for the structure without defects, we see that the Fermi energy level is close to the conduction band in the I layer, which means that the I layer actually corresponds to n-type behavior for the structure without defects. Now I already showed that by the introduction of these defects, now the structure with defects should demonstrate a behavior corresponding to p-type, or you can say it should demonstrate p-type behavior. So this is the structure with defects. You can see underscore defect over here. I go to tools, cut line, draw a cut line. Then I wanna see the energy band diagram of this structure with defects. Hit apply, and in this structure you see that the Fermi energy level is now closer to the valence band. So as compared to this one without defects, the structure without defect demonstrates n-type behavior, but for the reasons that I have already described, the structure with defects demonstrates p-type behavior. So that point is already verified. Now let us go to the code. It's already running. The structure without defects is now running. The IV characteristics under light conditions. Here are the IV characteristics of the solar cell without defects. And here is the power curve for the solar cell without defects. This once again is the structure under light conditions without defects, and here I can also go to display the contours, refine contours. Once again we can look at the photo generation rate across the structure. Here is the photo generation rate, hit apply. So you can see the photo generation rate under like in a linear way, or you can see it in a logarithmic fashion. You can draw a cut line over here as well. But more than the photo generation rate, I'm actually interested in looking at the recombination rate, because the recombination rate would actually incorporate the effect of the defects as well. So recombination rate under log condition, hit apply, click OK, and then we go to tools, cut line. So here is the recombination rate for the structure without defects, and then when it runs for the code for the structure with defects, this one over here, you can also see the code part where we have included the defects is still running, and because of the inclusion of the defects, it's gonna require more time to get simulated, so we will wait for that part. This is also simulated. Okay, here are the IV characteristic of the structure with defects, and then here is the power curve for the structure with defects. Okay, here is the structure. You can see underscore defect over here under light conditions with defects. So I go to tools. Basically I want to see the recombination rate for this structure with defects, so I go to contours, go to define contours, and I want to show the recombination rate for this structure with defects as well. Hit apply. You want to see it under log conditions. Okay, then we go to tools, cut line. All right, so here you can see underscore defect. So now I want to show you a comparison of the recombination rates for the structure with and without defects. Here is the structure with defects, and you can see inside the I layer the recombination rate is around 3 into 10 to the power of 20 per centimeter cube for the structure without defects. For the structure with defects, this recombination rate is 2, 3, 4, 5, 6, 7 into 10 to the power of 20 per centimeter cube. So the recombination rate inside the I layer is more than 2 times in the structure with defects. More recombination rate means lower performance of the structure with defects. And that would also be obvious over here. So here is the structure without defects, and you can see the short circuit current density, open circuit voltage, fill factor, and efficiency. Similarly, here is the code for the structure with defects. So I go to the performance parameters, so we can see the performance parameters over here, and then we can compare these performance parameters one by one. So defects in silicon solar cells significantly impact key performance parameters, which are short circuit current density, open circuit voltage, fill factor, and efficiency. Their effects depend on the defect type, concentration, energy level, and capture cross sections. And let me give you a comparison of these performance parameters. So let us first look at the short circuit current density. So if you compare the short circuit current density of the structure with defects, it's approximately 52.3 milliamps per centimeter square. Compare it with the structure without defects, and it's approximately 54 milliamps per centimeter square. So the silicon solar cell structure without defects has a higher short circuit current density as compared to the one with defects. What is the reason for that? So defects act as recombination centers, reducing carrier collection efficiency. Bulk defects lower minority carrier lifetimes, while surface defects increase surface recombination. And the effect of this is that it results in reduced short circuit current density as fewer photogenerated carriers contribute to the current. So the net effect is that the structure with defects is going to demonstrate lower short circuit current density as compared to the structure without defects. Now let us compare the open circuit voltage. The open circuit voltage for the structure with defects is approximately 0.49, while the open circuit voltage for the structure without defects is approximately 0.51 volts. So we can see that the structure with defects has a lower open circuit voltage as compared to the structure without defects. So actually higher recombination rates from deep level defects reduce the quasi-Fermi level splitting, and it also increases the leakage currents, and the effect of this is significant reduction in the open circuit voltage, especially with high defect densities or deep energy levels. We can also compare the fill factor for the structure. This one is without defects. It has a fill factor of 73.65, and the structure with defects has a fill factor of 74. So defects should generally cause non-ideal diode behavior, increasing recombination, reducing the shunt resistance, and higher defect densities also increase the series resistance. In this case they are comparative, but let us focus on the efficiency. The efficiency for the structure with defects is approximately 18.9%, while the efficiency for the structure without defects is approximately 20.4%. So the structure without defects has a much higher efficiency as compared to the structure with defects. Why? Because efficiency declines as the short circuit current density and the open circuit voltage degrade for the structure with defects. There is going to be radiation induced or metal impurity defects, which is going to worsen the recombination as well. So there is going to be efficiency loss in materials with high defect densities or after defect inducing processes like ion implantation, etc., oxidation, diffusion, etc. So in summary, defects act as recombination centers, reducing carrier collection, voltage, and efficiency while collectively degrading the solar cell's performance as well. I also want to show you a comparison of the internal and external quantum efficiencies of the solar cells with and without defects. So if we focus on this area, in this region around 0.55, and let me show the same value over here as well, so that we compare apples to apples. So for the structure without defects, our quantum efficiency is approximately 99%. However, for the structure with defects, our quantum efficiency in this region is approximately 92%. So there is a big gap in terms of the quantum efficiency as well. So overall we saw, and then you can compare the IV characteristics and the power curves for the structures with and without defects. So overall we can see that defects actually deteriorate the performance of the solar cell. Similarly, it also degrades other kind of semiconductor devices, for example LEDs and transistors as well. So that is pretty much it for this video. Thank you for watching this tutorial on simulating defects in semiconductors using Silvaco TCAD. I hope this video helped you understand how defect parameters influence material behavior. If you found this video helpful, don't forget to like, share, and subscribe for more content on semiconductor simulations and device modeling. If you have any questions or need further clarification, feel free to leave a comment below. See you in the next video. Adios.